I know he will be looking for it. Why is that still backwards? I have flipped that camera 3 times. But thank you. Right, Sean. But I am gonna give you guys the information after class. I'll get it all organized for you. Now that I have all your data. Okay? Good deal.
We did it. Yeah, we found. Yeah. I have one for My childhood was Thomas the Tank Engine. Go Diego, go.
Go Diego Go is cute. Yes. Who did what? Oh, Katie made them. They're beautiful. Thank you.
They are.
Yeah. That's awesome. Woo. That is darling. And those look delicious. I'm gonna have to eat them. All right. Come on. Okay, so redux. Redux. This is the way of redux. Okay, are y'all situated? No, Cole's coming. All right, well, he'll get here. He lives here. Yeah. So you have to see a redox reaction. You see redox reactions every day anyway, and some of them are happening around you that you don't see, but super common, super common. And some of the types of reactions we've already learned about are also redox reactions. So this is a complicated lab, as you saw. Not too complicated to run necessarily, but fairly complicated to set up and take down and get accurate data. So that one took a long time. So I'm glad that was over. Setup was like, oh, please, it never ends. So redox reactions are electron transfer and chemical reactions were the last two sections of your chapter here, right? So oxidation involves a loss of electrons. And then reduction is going to involve a gain of electrons. So it seems a little backwards when you use the word reduce and then you're talking about it gaining electrons at the same time. So there are some great little memory mnemonics in here that I'll be showing you guys that will help you remember. But if you think of it like a number line and you think of the charge, like +2 or negative, +2, -2, whatever, then it makes a little more sense because when you gain electrons, your charge gets more negative. So you actually are reducing the charge, if that makes sense. So the charge reduces, it gets more negative, but you are gaining electrons. You're just gaining the negative subparticle. So oxidation is the gain of oxygen or the loss of hydrogen and the loss of electrons. So we used to define oxidation as the gain of oxygen, which is where the term comes from. But now we've better defined it as the loss of electrons. And then reduction was the same way. We now define it instead of as the loss of oxygen, which if you're saying reduction, when you're losing oxygen, you're reducing. We now refer to it as the gain of electrons. So the terminology didn't change, the definitions changed, which added, I think, to the confusion a bit. So they always occur together. When something is oxidizing, something else is reducing, always. So because they occur together, instead of saying, oxidation, reduction, reaction every time, we just call it redox because it's just so much easier to say redox, right? So redox reactions are reactions in which one species is reduced, another is oxidized, and the oxidation state of the species involved changes. So this I had to share with you all because I was randomly looking up images to throw in the slideshow. And this is from a strange cartoon from the Azerbaijan Chemical Society. And I am entirely unsure why they chose to animate it this way, but I don't think you'll forget it. So this is a GIF actually from the Azerbaijan Chemical Society. So, I'll just take these and eat them. And then I'll change color. Oh. And then these two run off together. Anybody know what's going on? Because I'm not entirely sure. But
I don't.
so you got zinc. Okay, so you got zinc, and it's gonna displace the copper. So he's kicking copper out, right? Boom. Copper is so sad, but he eats these two electrons here, and now he's happy. And then zinc says, all right, I'm gonna go hang out with sulfate.
I don't want to go.
But I just had to share it because it was the weirdest thing. There are some weird things on the internet. I'm sure y'all know this is not as weird as some things I found, but that was weird. So I sat there and stared at it and played it like 4 times. And then I thought, you know what, I'm gonna put that. Don't even know what that is, but I'm putting it in the slideshow because it's too weird. So here are some ways to remember redox reactions. If you can remember any one of the next 3, you'll have it. Okay, so this is the old school one, is oil rig. And they use oil rig because you can say oxidation is loss of electrons and reduction is gain of electrons. But you have to remember the of electrons part. Like if you start thinking oxygen, you're going to get it backwards, right? So your oxidation is loss of electrons. Your reduction is gain of electrons. So oil rig is one of them. Oil rig's the one that they had when I was in school. I always heard oil rig, but I also heard this other one, and I like this one too. This one I like because it includes the word electrons. Does anybody want to guess what Leo says GER is? If I've told you it includes the word electrons.
Loss of electrons is oxidation.
There you go.
Something like that.
Yep, you got it. Yeah, loss of electrons is oxidation. Gain of electrons is reduction. So if Leo says GER, and sometimes they just say Leo the lion GER. It's easier to say Leo says GER.
No.
But it actually, Ozzy, yo, hey. Do not yell at his lunch. No. So yes, your loss of electrons is oxidation. Your gain of electrons is reduction. And then there's this one, which is totally weird. And I just found it last week when I was looking. Never seen this one before, but electron loss means oxidation is Elmo. And honestly, if you didn't read that phrase in his voice, there's something wrong with you. Because if you didn't hear that little Elmo voice saying electron loss means oxidation, then what's wrong with you? Because, I mean, come on. But there isn't another Muppet or Sesame Street character for reduction. There's just Elmo. But I guess that works for some people. No, you're not eating people's life. No. So I've never heard that one until recently, but I thought that was strange, so I would share it. Electron loss means oxidation, Elmo. So if you can, exactly. I asked the other group if anybody remembered the name of Elmo's fish. Please tell me somebody remembers the name of Elmo's fish. I'm sure you put your parents through hours and hours of Elmo every week.
Never watched.
Dorothy, his goldfish.
That makes sense. It was.
He'd go, hello, Dorothy. Every day he'd ask her a question. And she, of course, would just swim around because she's a fish.
Sesame Street.
By the way, we do have a new fish, if y'all didn't notice, because Herschel kicked the bucket and, well, Herschel went to the great toilet bowl in the sky. And we replaced him with this Bunsen. But Bunsen came from a beta breeder. So hopefully Bunsen will be better than Herschel. And actually, he is already smarter. Like he has learned that if I tap lightly, it means come up to the top. And he can feed himself because Herschel apparently was not smart enough to know that if you go to the top and open your mouth, the food, that's how you get it. And if it sinks to the bottom, you have to go down there and suck it off. Like he couldn't figure it out because he was always starving. And then he ate his own tail and then he couldn't swim to the top to get food. So, I mean.
He ate his own tail.
You didn't notice it was gone? He ate his own tail, Ethan.
That fish is smart.
I looked it up because I'm thinking there's no other fish in here. So another fish didn't do it. And it doesn't look like there's any kind of weird, how would he get a weird bacteria? Like he's not coming in contact with anything. So I researched it. Beta's tail disappears. And it's like, oh, your beta might be bored. And he ate his own tail. Apparently it's not that uncommon because there are other people whose betas have eaten their own tails. So we have Bunsen, and hopefully Bunsen will not eat his own tail because he's really lovely. So here are 3. I know, right? I know. So here are 3 memory devices. You got your oil rig, your Leo says GER, and then your Elmo. So then if you just go with your oil rig, you get oxidation is loss, reduction is gain of electrons. So do it this way. If I say reduction is, you would say reduction is gain of electrons, which makes the charge more negative. So oxidation is what? Loss of electrons, which makes the charge more. There you go. You got it. So oxidation numbers. This part gets a little odd. So there is a really involved chart that can go with this, but periodic table can make it easier. So your oxidation number, which is also your oxidation state, you guys good over there? Is the total number of electrons that an atom either gains or loses in order to form a chemical bond with another atom. So there's this very handy dandy, super detailed chart, which you can follow to determine the oxidation number, right? So if you go into higher level chemistry, this is the kind of stuff that you would probably memorize, but you would also probably understand it at such a deep level that you didn't need to memorize it. Like you wouldn't have to think about it. You would understand what's going on so much because you would be so into it. I don't want you guys to have to memorize it. I want you guys to understand the concept of reduction and oxidation based on electron loss or gain. That's the big thing for you all. If you keep going further into chemistry, it'll get super involved. But another way to find oxidation numbers, an easier way, kind of a basic equations and nothing kooky, is to look at the periodic table and remember how we organize the periodic table by the number of valence electrons, right? So who were these guys here? These orange ones. Noble gases. Okay, who can remember what's special about noble gases?
They have complete shells.
Yes, they do. They have a complete set in their outer valence shell, right? So that means one of the kids in the junior class said their friends list is full, which was kind of a good way to think about it. They don't have any friends they want to get rid of, and they don't have any friends they need to gain. They are happy as can be, right? And because that, they're very non-reactive, remember? Very stable and very non-reactive. They keep to themselves over here. But if these guys are full, then these guys are one less, right? They have one less electron.
They're the halogen.
Yeah, there you go. So see, I have one less, two less, three less. And then depending here on what row they're in, it's 2 or 4, right? And then the same sort of thing here. These guys have one more. Bless you. One more electron and one more. So these are oxidation. This is another way to kind of see where oxidation numbers would go, right? And I'm not going to expect you guys to do lots and lots of oxidation number equations because it's hard. So how to identify a redox reaction? So oxidation and reduction must both occur in a redox reaction. They always go together. Always, always, always. So if one particle gains electrons in a reaction, something else has got to lose it because you've got your law of conservation of matter, right? I mean, you're not going to be creating and deleting electrons from the universe just for the heck of it. It's got to come from somewhere and it's got to go to somewhere. So you look for changes in the charges. So if you look at this one, it says, how do you know it's a redox equation? So if you look right here, you've got your 2 hydrogen pairs. So it says, what is the charge of H2 here? Well, that's a 0. And what is the charge of oxygen here? That's a 0. So what is the charge of hydrogen? And then oxygen.
+1.
There you go. +1 hydrogen. So think back, how does hydrogen bond with oxygen? And why do you need 2 hydrogen for every oxygen?
Because the hydrogen is +1 and it has to equal 0.
Yes, because the oxygen is -2. You got it. And the hydrogen is +1. And there's 2 right here, right? 2 hydrogens. Right, right here, 2 hydrogens. So this is a redox reaction because atoms are being reduced. Oxygen gained 2 electrons to go from 0 to -2. And oxidized because the hydrogen loses 1 electron and goes from a charge of 0 to +1. So right in there, we've made water and it's redox, right? There's redox everywhere. So this is half equations. Y'all saw the bit about half equations, right? I mean, half reactions. Did it get, was it clear or was it kind of like, what in the world am I looking at? So basically your half reaction is, it's either the oxidation or the reduction component. And it's easier to pull them out and work them separately as a half reaction. So you would do the reduction part and the oxidation part separately. And this is a quick little show you how to do it video. Do I have sound? I do.
It's not Professor Dave.
This is not Professor Dave. And this is the one with the lady. I really tried to place her accent. It sounded Indian, and then at times it sounded like my South African friend, so I was very confused, but good example.
In this video, we will learn how to write half equations for simple redox reactions. A half equation shows what happens at one
She also likes to spit on the microphone.
during electrolysis. So we do need to be able to complete and balance half equations for these reactions. Remember that oxidation occurs at the anode and reduction occurs at the cathode. Let's have a look at a simple redox reaction. A strip of copper wire is placed in silver nitrate solution.
Now, do y'all remember that reaction?
The solution
We did that at the beginning of the year, and it was a double displacement. So think about it. If it's a double displacement, in this case, it's actually also a redox. It's not one or the other. It's both. But do you remember what happened when we put the copper wire in the silver nitrate?
It grew silver all.
Yeah, it looked like hair, right? Yeah, it grew silver all over it. Well, here it is.
color from colorless to bright blue. You will also observe silver metal crystal deposits on what was once copper wire. Why is the solution turned blue? Pause and think.
Pause
Copper
on there.
nitrate.
This is a single
Yeah.
displacement
There you
reaction.
go. Play.
Copper
Hello.
metal, which is higher on the reactivity series, has displaced silver in silver nitrate. The
So there's your
solution is turned
displacement.
blue because of the copper 2 ions in the solution. This is also a redox reaction where reduction and an oxidation are occurring simultaneously, hence the term redox. Remember that oxidation means the loss of electron and reduction means the gain of electrons. So for a redox reaction, electron transfer has to happen with one substance losing electron and another substance gaining electron. The silver nitrate is an ionic solution containing Ag positive and NO3 negative ions. So here is the equation again. All the ions shown separated. The copper metal has been oxidized because it has lost 2 electrons to form Cu2 positive ions. If we take out this half reaction, we now have a half equation, whereas the silver ions have gained electrons to become reduced, represented by this half equation. They are called half equations because each equation represents half a redox reaction, either the reduction reaction or the oxidation reaction. When the two equations are added together to form the final redox reaction, you can see that everything, including the number of electrons, are balanced. To reform the ionic equation, the electrons are equal on each side and can be removed. What about those nitron ions in the original equation? As the nitron ions appear on both sides of the equation, they're called spectator ions.
Y'all remember those,
as they
right?
have no effect on the overall reaction.
They just watch.
Much like spectators in a football match have no effect on the final result of the game.
European football.
Here is another redox reaction where the iron free chloride oxidizes iodide ions to iodine solids.
With the microphone.
See if you can write the two half equations.
So watch what she
Pause the
does.
video and work out the answer.
So right here,
Did you get it?
she's going to take the reduction portion. All right. And it's going from 3, positive 3 to plus 2. So it's going from plus 3 to plus 2. And then this one's going from negative to positive, right? So if you want, boom, there we go. I'll pause it there. So to go from plus 3 to plus 2, you had to add an electron because it's one less. So it's gaining an electron. So it's reducing, right? And then on this side, yep, we lost 2, right? Because it's the coefficient. You got to remember the coefficient. So on this side, he lost 2 electrons, right? Okay, hold on.
Iron is reduced and so gains an electron.
Just to balance it?
The plus 2E. Which one? Where? Here? No.
Under oxidation. Plus 2E.
Oh, so what they're doing is they're showing what happened here. This is what's going to happen on the other side if you were balancing. Yes.
Yeah.
This is breaking this out, showing how it becomes that.
Yeah.
Basically, your iron 3 plus ion, right? You're adding an electron, and that's going to yield or result in your plus 2.
Iodine ions are oxidized and so lose their electrons to form iodine. So in summary, half reactions represent either an oxidation reaction or a reduction reaction of a redox reaction.
Can anybody place that accent? It's weird, wasn't it? What was that?
What's the thumbs?
Well, I think she was awfully close to a microphone when she recorded it, but it was very clear. So I looked at a bunch of them. A lot of them are really long. So I was trying to find a shorter video. So that was a good shorter one. So yeah, like, I can't place the accent. It's killing me. Like, it sounded Indian. And then she would say, like she said, separate and affect. And she said them just like, I have 3 South African people that I know, and it sounded just like the way they say
Maybe
those
she'll
words.
learn those words from South African people.
Maybe.
Something
South African is a strange accent, if you've ever heard it. It's a mix of, it sounds sort of Australian, but not Australian. And so, how would you describe it, Cole? Kind of. It's an odd accent. It was funny because one of my South African friends was at my house one. I think it was Drew's first communion party. And she was there, and my father-in-law, who is like one of the absolute smartest people on the planet, he's staring at her while she's talking, like he's staring at her across the table, and she's loading up her plate, and he goes, I can't place your accent. Don't, granddad, don't tell me. And he's staring at her, and he said, it's not New Zealand or something, is it? And she said, you're in the right hemisphere. And then it was like his face went, like he was really trying to figure it out. And then finally he went, South Africa. They carried.
Did Britain colonize South Africa?
It's a lot of Dutch, actually.
Yeah,
So yeah.
They tend to like say like
Mhm.
I have a friend whose parents are South African, and he
Yeah.
like he doesn't have the accent, but he definitely some of the words he'll say like supper instead of dinner.
Yeah.
Like he'll just pick up tendencies. I'm like, dude, it's like.
Well, and there are dialects. There are different dialects of Afrikaans, which is the language they speak. So the white South Africans speak Afrikaans, and it's like a combination of languages. But there are different dialects of Afrikaans. So like one of my friends and her husband speak different dialects of Afrikaans. Really, like, could we get any weirder? Yeah. So identifying your redox agents. You good back there, Cole? Jack? Everybody's here. Okay. Identifying agents in redox reactions. So your oxidizing agent is the one that we used to say it adds oxygen, but it doesn't always add oxygen. So we can say it removes hydrogen. And if it's oxidizing something, it's removing the hydrogen, which means it's removing what?
Electrons.
Hey. All right. And then your reducing agent, we used to say removes the oxygen, but now we say adds hydrogen. Oh, is this confusing or what? Reducing, adding, removing, adding. Right? So what did the oxidizing agent say to the reducing agent?
That's not funny.
Your loss. I like the cat science dad joke memes.
That's rude. That's oddly specific.
I don't even love cats, but I like this cat. Like, this cat is funny. This cat is entertaining, people.
I love how you just like escalated that step by
He
step.
totally did.
Like, it's not
So, okay, balancing redox reactions with half equations. So this is what we just had in the video. All right, Cole, you with me? All right, so this was what your book gave you, this big long list of things, right? So you identify the reactants and products. You write an unbalanced equation in ionic form. You exclude any spectator ions. So it's a lot of steps. Y'all are so goofy. But this is good to refer to. So if you're doing these equations for homework or for a lab, these little skills toolkit things that are in your book, so cutesy. Skills toolkit and a wrench. They're actually really helpful because it gives you nice, clear Ozzy. Good Lord. Gives you nice, clean steps. So I liked this guy too. Come here. This guy did, it's not Professor Dave because all of Professor Dave's redox videos were a little long. So, well, I know, but I didn't want them to take up too much time.
Haircut or after haircut?
They were pre-haircut, which are my favorite. I like the pre-haircut best. I've never noticed his chest hair, Cole. I've never noticed that, I gotta say.
You notice his chest hair, bro. Like, what's up with that? I'm sorry, I thought this was are you staring at Professor?
Do we need to have a talk?
Cole,
No, it's
look
funny.
at you any differently.
Yeah.
We'll treat you the exact same.
Okay.
Oh my gosh. Bro, are you thinking of Professor Dave's chest hair? Is that what you said, right? Like, take a deep breath.
I seriously didn't notice. Really, like I've never. Yeah, he does the red thing. Yeah, okay. Shannon's gonna watch this back and think we're all insane. She knows.
Well,
we're
now,
crazy.
now,
You already know.
now I have to look at it.
Yeah, now next time I'm gonna. So Cole, in which video was it most prominent? Because I want to go look. Like,
Cole should know the exact one. He remembers it.
At what time? Like, what
we'll look
minute?
after the lesson. All right, so.
Professor Dave's chest hair.
You are, this is almost better than the time I drew cleavage on the whiteboard in front of a room full of middle schoolers. That was great. Okay, I'll do that next year too. Yeah. When I what?
You were trying to describe gasoline.
Yeah. No, I did. When I was teaching middle schoolers life science and I was talking about cell division and I was like, there's, anaphase, metaphase, telophase, and then you get here and so I drew two circles with little nuclei inside, two little cells, and they were kind of connected. And then I said, and then, when they break apart, it's cleavage. And I drew the line right down the middle. And then I realized what they looked like. And the whole classroom instantly saw it the second I said the word cleavage. And this whole room full of middle schoolers just lost their minds.
Like,
And
you have that just shape, and then you say cleave, and then it's
Yep,
all over.
yep.
We're all
yep. So now I do it on purpose because it's worth it. So. All right, so I have reactions. Let's look at this guy.
Haircut to chest hair.
Welcome back to the second part of the series.
All right, so this is a good one. Let's watch this.
Of balancing aqueous redox equations. We ended off with the following question. We're asked balance the redox reaction in acidic solution. We'll follow the exact same method as we did in question number 1. First, we have to determine what's being oxidized and what's being reduced. And we learned that if we're dealing with atoms that are in their solid state or pure gas molecules, their oxidation states are 0. So I'll start by placing 0 here, 0 here. Notice that the hydrogen ion, this one, is going from plus to 0. This means that it is gaining an electron. If you have a gain of electrons, that is a reduction. So this is being reduced to H2.
What's the matter?
Got one hydrogen and one chromium on the left, but two hydrogens and two chromiums.
He'll get there.
Two hydrogens on the right.
No worries.
So going from 0 to 2 plus, it is losing electrons. So we say that there's an oxidation happening here. Let's write those out exclusively. So we have oxidation, O. We have Cr solid, and that is forming Cr2 plus. And for the reduction, we're going from H plus aqueous over to hydrogen gas. Now we need to balance this in 2 ways.
So here you go, Alex. Here's your balancing. Yep, dude. Talk.
This is by mass.
Yo,
And
dude.
as you can see, we have one atom of Cr and
Hold on.
one atom of Cr2 plus.
Wait a minute. Stop it.
This is
No.
by mass.
Okay,
And
here
as
we
you can see, we have one atom of C.
Why do you do this? Why do you do
Now
this?
we need to balance this in 2 ways. The first way we balance this is by mass. And as you can see, we have one atom of Cr and one atom of Cr2 plus. They're technically balanced. And to balance the second equation, we will place a coefficient of 2
So
in
there you
front of
go.
the H plus ion. Now both are balanced. The other form of balancing involves charges. Here we have a 2 plus charge, and here the charge is 0. So to balance this out, I'll write down plus 2 electrons. And over here, since we have essentially a charge of 2 plus, I'll write down plus 2 electrons. At this
So
point,
that's
we have to make sure that the charge in the oxidation and the reduction equations are equal. This one has a charge of 2, and this one has a charge of 2, so we can proceed now to adding up these two equations and canceling out where there are commonalities in the products and the reaction side.
Come on.
Two electrons here, two electrons here, they will cancel out, and you add the products together.
Hey.
You get a product of C1,
You don't help. Go ahead.
H plus ions, reactions in both
He's a spoiled brat.
reactions, and our products were Cr2 plus, aqueous, and one molecule of H2. That right there.
See it? Oop. Okay, so you see what he did despite the goofy dog. So this and this here, these canceled out, and now he's put in his coefficient.
Hence, the balanced redox reaction for this example in acidic solution. If you have any questions about what we just did, make sure that you write a comment below. Or use
So
the
we
website,
balanced it, like Alex was
bioexample
saying, he didn't deal with the
forms.com.
coefficients.
We'll see.
He did, but he broke it out into half reactions first. And then he balanced coefficients, and then he balanced charges, and then he put it all back together. So that's the basic premise of half reactions. So then your book goes into a little bit of electrochemistry, right? Now, next week, we're going to do electrolysis of water. So next week, we're going to take liquid water and use electricity and turn it into hydrogen and oxygen, which is super duper fun. So are you right there, Alex? Alex has lost it. All right, so
I've lost.
electrochemistry. I'll get that out of the way a little bit. So chemistry meets electricity, your book says. Electrochemistry is the branch of chemistry that deals with the chemical changes produced by electricity and the production of electricity by chemical changes. Oh, what does that say? This sounds, when I read this definition, I'm instantly reminded of anything written by Paul in the Bible where he repeats the same phrase 10 different ways. I don't know if you've ever noticed that, but he'll be like, the eagles flew today. Verily I said, flew today were the eagles. And it's like, that's what he does. So the branch of chemistry that deals with electrical changes produced by electricity and the production of electricity by chemical changes. So we have, if it would go. So electrical pressure is expressed in volts. Do you guys remember this? Those of you who did physical science with us last year, the electrical pressure is described in volts. So voltage is the potential difference between two electrodes. And it's a measure of chemical potential for a redox reaction to occur. So the pressure from an electrical circuit's power source that pushes the charged electrons through a conducting loop, enabling them to do work like illuminating light. That is voltage. Do you guys know? Okay, so this is a great picture, by the way. So I don't know if you remember ohms, but ohms were resistance. For those of you who did physical science with us. So ohms were resistance. Here's your amps. This is basically like your current going through here. And then your volt is just shoving because that's what it is. It's the pressure that pushes the electrons through. He is just, I know, he's not being friendly about it either. Like he is, get through there, you're being shoved. So y'all know, do y'all know where the term volt comes from? Do you remember?
What's the name of?
It was the name. I'm gonna get it wrong if I don't look it up. Do you know his full name? He has one of the best names in all science, and I love good science names.
If I had to guess,
It is very long.
British or German?
Hang on, I will tell you. Okay, his full name was
I don't know.
Count. It starts with Count, so you know it's good.
Or else.
Count Alessandro Giuseppe Antonio Anastasio Volta.
Bro, that is a name.
say, oh, you know, Volta. And I'm like, no, it doesn't count. Alessandro Giuseppe Antonio Anastasio Volta. That's a name. 1, 2, 3, 4, and then a last name and a title. So Count blah 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 blah. Count Volta. Anybody named Count Ozzy? You got it. Ozzy. Nobody's playing with you, baby. I know you want. He's just throwing that bone, hoping somebody will.
It's the purest form of self-entertainment. You just throw a bone.
He plays like that. He will entertain himself all day. He'll throw bones, balls, toss them up in the air. Weird
Very
dog.
smart.
No.
It's also very loud.
Yes, it is. Can you do something with him, Cole? All right, so your electrochemical cells, these are your batteries, right? It's a device capable of either generating electrical energy from chemical reactions or using chemical energy to cause, using electrical energy to cause chemical reactions. And you guys remember electrodes, right? This is the point where current enters or leaves the electrolyte. So you have electrodes on the ends and electrolyte in the middle. You remember what an electrolyte is?
Yeah.
What is it?
A metal or iodine.
Yeah, it's typically a liquid, a fluid with, and not always, usually, and what's in it though? Ions. We have ions in it, right? We need the ions in it because that's what helps the electricity flow. So when you drink a Gatorade, all right, or a Powerade or whatever, it has usually some potassium and some sodium in it, but those are ions. So why do we need that? Because your muscles function on electrical impulses. So the more ions you have, the better you are at transmitting those electrical impulses. That's the idea. But you get sodium and potassium from everything that you eat normally anyway. So you have, do you remember the names of the electrodes?
I do.
Yeah.
Cathode and anode.
Cathode and anode. Yep. So you have a point where the current enters and leaves the electrolyte or your electrodes, and it's a solid electric conductor that carries electric current into non-metallic solids or liquids or gases or plasmas or vacuums. And it's a terminal through which the electric current passes between metallic and non-metallic parts of an electric circuit. So you got your metallic parts. Are you okay over there? You got your metallic parts on the ends and your electrodes are the connectors. And then in between is the electrolyte, which as it points out can be solids, liquids, gases, plasmas, vacuums, whatever. And that has the electrolyte in it. And then your cathode now is where the reduction occurs. When you're looking at a battery, like this battery right here, and there's this little button on an end and a little like a rivet on the other end. Which end is the positive end? The little button end, right? Okay. And is that an anode or a cathode? Yeah, because cats are positively, yes, there you go. All right, there you go. So you've got your cathode is where your reduction occurs. So the cathode is an the electrode of the electrochemical cell at which reduction occurs, and your anode is where your oxidation occurs. So we did oil rig a minute ago, right? So this says that your anode is where your oxidation occurs. And it also says at the anode, anions, which are negative ions, are formed by the electrical potential, right, which involves your force. So there's your voltage, right, to react chemically and give off electrons, which is oxidation, which flow through the circuit. So we did oil rig a minute ago, and it meant what oxidation is. Oxidation is loss of what? Electrons, which makes it more
Positive.
right. And then reduction is gain. That's it. And then what was Leo Ger? Loss of electrons.
Loss of electrons reduction.
Loss of electrons is oxidation. Gain electrons is reduction. So those were the helpful things to remember oxidation reduction. So how do we remember where your oxidation and reduction occur when it comes to anodes and cathodes? Okay, so we have some good ones for those too. So the cathode is where reduction occurs. The anode is where oxidation occurs. So we get this phrase, anox red cat. Doesn't really mean anything. It's just anox red cat. And well, it's just anox.
That looks more like a water buffalo.
He's just he does look like a water buffalo.
That's the horns.
I know. But he's anox, and that's a red cat. So, Anox red cat, anox red cat. So if you can do the anox red cat, which is kind of a weird one, but it will help you remember that cathode is reduction, the anode is oxidation. So it's like oil rig, Elmo, all these other fun ones. Leo says grr, grr, Leo. I know, United in Elmo's world. And I don't know why he looks so confused either. He's a very confused ox.
That man's eyes is doing a
It looks like
split.
he's riding.
Have you ever seen, there was the old SNL skit with Tracy Morgan would play Brian Fellows. He was like the one of those nature guys that brings animals out on the show, but he was like a total idiot. And they brought, well, no, he wasn't, sorry. He was the host of a show and somebody brought the animals out. That's what it was. But he was still a total idiot. And they brought a goat out on stage and he kept saying, that goat got devil eyes. And then I looked at him and that was my first thought, is that goat got devil eyes. If you've ever looked at goats' eyes, they are weird, man. They're freaky looking. So yeah, they don't look like our eyes. So. All right, so then you have your complete cell. So your complete cell, here's a good example. So if you ever wondered what's in a battery, this is what is in a battery. Now, if anybody ever taken a 9-volt apart?
No.
So it's odd because inside of them is just a stack of like button batteries, turned this way and then turned that way. It's not, it's really weird. It's not what you would expect to see. It's not at all like this would be. So in this situation, sorry, you've got what they're calling an insulating washer. I suppose that has a name, that solid piece on top, and then a wax seal and all this stuff. You have a sand cushion, a carbon rod. I have not dissected a battery because I'm afraid I would hurt myself, but that's pretty cool. Uh-huh.
Is the wax seal
It should be non-conductive, so yeah.
then the wax seal goes on, the insulating washer looks to go on top of the carbon rod.
Yeah, so you've got the carbon rod and then it looks like it connects completely to that cathode.
Is it metal conductive, not insulated?
No, the metal's conductive, yeah, but it means the conducting is only coming out of that little cathode button and not all over the whole top. You ever get one of these regular like AA's or whatever with the button on it and you don't have it lined up perfectly and it won't go? Like you have to have the little button lined up just right, right?
Yeah.
So this wax seal is doing the job of, I guess, keeping this washer, the wax seal, and then whatever this was, porous separator. I don't even know what a porous separator is made of, probably some kind of a paper or something. But this battery has in it zinc, and most of them do, most of the ones that we use do. And then there's all kinds of other types of batteries too, right? I mean, like you have batteries that can be recharged, and you have the lithium ion ones that they get terrified about on airplanes. And
I don't blame them
Well,
considering what they.
what was it? A couple years ago, there was some product. It was a Christmas thing. Y'all probably don't remember, but whatever it was something everybody wanted. It was like the hot item of the year.
I think
And
there was like a hoverboard or something like that.
yeah, yeah, maybe. And the lithium ion batteries were just catching fire. I think it was a hoverboard.
And then one of the Samsung phones.
And something else, what was it?
Samsung phones.
The Samsung phones, yeah, just catching fire. Just,
Forever ago.
yeah, because they just get too hot.
Samsung phones.
That's not. I don't want that. Hmm. So, you got pathways for moving charges. All right, what does that mean? So in any electrochemical process, electrons flow from one chemical substance to another, driven by an oxidation reduction reaction. So a redox reaction occurs when electrons are transferred from a substance that is oxidized to one that's being reduced. The reductant is the substance that loses electrons and is oxidized in the process. The oxidant is the species that gains electrons and is reduced in the process. The associated potential energy is determined by the potential difference between the valence electrons in atoms of different elements. So wait, if the reductant is the substance that loses electrons and is oxidized, what's the reducing agent?
The reducing agent, they believe, is the reductant.
Yeah, so look at the definition. The reductant is the substance that loses electrons and is oxidized. So where did we have our definition of reducing agent?
I don't think you can.
Yeah, we did. It was up here. Where was it? Where was it? We had it.
I don't know if we actually
I
had
thought
it.
we did. Maybe not. Maybe
Yeah,
my other group had it. I was gonna, oh no, there it is.
well,
Reducing agent removes oxygen from another substance or adds hydrogen to it.
So that means it would lose
It adds
hydrogen. and
hydrogen.
lose electrons.
Right, there you go.
So if it loses electrons,
So it
that means
adds hydrogens, which means it loses electrons.
it loses electrons
Where were we? We were here.
here.
Okay.
You added Neutron to your shopping list.
How do you buy one of those?
I would love to know.
Alexa,
What store sells that?
how much is a neutron?
Do you want to know the price for Neutron?
Yeah, I do.
A top result is Jimmy Neutron, Sea of Trouble. It's $9.99.
Mom, you're
Thank
watching.
God.
Alexa, neutron should be $0.
Sorry, I'm not sure.
That's what I thought.
It's like-
Yeah, I know. Alexa, remove neutron from my shopping list. Weirdo.
I couldn't find Neutron on your shopping list.
What is wrong with her? Okay,
She's too busy spying.
right. I know. So we have
Like that meme.
two types of electrochemical cells. All right, two types of electrochemical cells, galvanic cells and electrolytic cells. So ahead of next week's lesson, here is a heads up on Luigi Galvani. Okay, Luigi Galvani obviously discovered galvanic cells. So this is fun. All right, you guys have to watch this bit on Luigi Galvani because I don't think your book told this story. Yes.
Okay. I can't believe I'm gonna say it. You say it. It was your idea.
What?
Where's Mario? There's Luigi.
Where's Mario? Oh, this guy's way ahead of Mario. All right, so this one's going to be interesting, y'all. For real. You won't forget this.
How did Galvani make a dead frog jump? And how does that lead to the battery?
Whoa, what did she say for those of you who can go through it? How did Galvani make a dead frog jump? That's what she said.
I won't forget her face.
All right, so listen, because she has some animation, but you get to look at her while she yells at you. But for real, the story is great.
How did Galvani make a dead frog jump? And how did that lead to the battery? And hey, didn't a guy named Volta invent the battery? Well, I'll tell you, and along the way, I'll talk about professional misconduct, a surprising accident, the inspiration for fragrance,
Hello.
Strange.
Very
and
nice.
the building blocks of life.
Here we go.
Ready?
Yeah, inspiration for Frankenstein. For real. This lady likes electricity a lot. Jim has a jingle.
Sometime in 1790 or 1791, an Italian anatomy professor named Luigi Galvani was playing with electricity machines and hoping to find something interesting to publish. See, Galvani was a member of the Academy of Sciences at the Institute of Bologna, and he to submit a research paper every year. For the previous 4 years, he had published research on the hearing of various animals. However, that year his work was stolen by a rival, so he needed a new research subject, and quickly. Therefore, he turned to the subject of electricity and got several assistants to help him. He had static electricity machines that you could spin to produce large static charges, and jars called Leyden jars that could store the charge and give it in a terrifying jolt when you connected them in a circuit. One day, unrelated to his electricity experiments, he happened to put a dissected lifeless frog on the table while his assistants were running these electrical.
Okay. You hear what she just said? One day, she said, one day he happened to put a dissected frog on the table
As you do.
while his assistants were running electricity experiments. Oh, no. This gets better. Okay, wait, listen. You don't want to miss it.
Assistants were running these electrical experiments. He never said why he was cutting up frogs in the first place. A popular myth is that he was making frog soup for his sick wife. However, it seems much more likely that he was dissecting the frog for anatomy lecture. He was an anatomy professor after all. Anyway, there was a dissected frog on the table. Here's how Galvani described what happened next. Quote, I had dissected and prepared a frog, and I had put it on the table where there was an electric machine. As soon as one of my aides, by accident, touched the infernal nerves of the frog with a scalpel, at once he saw all the muscles go into violent convulsions. Galvani was deeply surprised to see the headless frog jumping, and did a series of bizarre and macabre experiments with frogs in a jar, frogs in a circle, to determine what would make the frog fail. Galvani, or honestly his assistant, discovered two things with this experiment. First, they found that frog legs are an extremely sensitive machine for sensing electricity, superior by a factor of 5,000 to anything non-biological available at the time. Secondly, and more importantly, Galvani started the study of how electricity works in living systems. He found that muscles contract with electricity and nerves send messages with electricity. In truth, electricity is the building block of living systems. We think with electricity, we hear and see and smell with electricity, our hearts pump with electricity.
What is happening?
That's a
Yo, Colin, I was like, I just
This is not just true for frogs. All animals body with electricity, our hearts pump with electricity, and our muscles move with electricity. This is not just true for frogs. All animals' biological systems are electrically based. Now, it took a further 150 years to truly understand the complex beauty of the biological system, but Galvani started us on that path. Galvani then decided to move his frog experiments outside to see if thunderclouds could make the frog jump as well as static electricity would.
Why not?
This was 38 years after Benjamin Franklin flew his kite in a storm, so he's not surprised at all to find the frog jump theatrically in thunderstorms. However, something else happened that was truly unexpected. Sometimes the frog would jump on clear days with no static electricity or atmospheric electricity involved at all. What was going on? At first, Galvani wondered if the frog stored electricity from past atmospheric storms.
Like a battery.
However,
Oh, come on. What's with the sound? Do that.
he realized it had nothing to do with the weather. If the frog
Here we
stored
go.
electricity from past atmospheric storms. However, soon he realized it had nothing to do with the weather. It had everything to do with his garden. See, Galvani had iron railings.
That is a
around
great
his garden
picture.
that he hooked his frogs on. He also used
That's
copper
awesome.
to transport the frogs.
What
It
in
was
the
this
world?
combination, the iron and the copper, that caused the frog to convulse.
What?
When he took the frog inside, he could make a frog dance with just a piece of copper and iron. Crazy, huh? This is a major find. Putting copper and iron into a frog produces electricity with no rubbing blows or thunderstorms in sight. Galvani decided that the frog moved because it had been alive in the past. He thought he was reanimating the frog, a la Frankenstein,
Mhm.
whose author was inspired by Galvani's research, by the way.
There you go.
Galvani published his work in 1791, and it was an international sensation, especially among anatomists. Suddenly, there was a way of studying
Okay,
how
yeah.
muscles move and how nerves communicate. He had connected electricity to what makes things alive. He had made the spark of life literal. Galvani didn't know it, but he had also invented the first battery. The acid in the frog leg reacted with the copper to add electrons and reacted with the iron to remove electrons. The electrons then flowed through the frog leg from the copper to the iron, making the frog leg jump. In terms of physics, it was a completely useless battery as it discharged inside itself. This is why most people don't consider his invention a battery. However, there was a man named Alessandro Volta who
That's the name.
You didn't say it. You left out some names.
Italy's leading expert on electricity. This is why most people don't consider his invention a battery. However, there was a man named Alessandro Volta who was supposed to be Italy's leading expert on electricity. He became obsessed with jealousy over Galvani's fame, which led him to inventing the first non-biological battery. This was the battery that changed the world. And that is why batteries are measured in volts in his honor. And that crazy story is next time on The Secret History of Electricity.
Yeah.
Well, the first
So,
battery
frog legs.
was made from dead frogs
Yep.
and metal.
Yep.
And then he
So-
created the battery out of jealous. I have real questions about
You have real questions?
I
No, nothing to question there. It was all totally normal, especially hanging the frog legs on the fence. That was completely normal behavior.
I'm not gonna lie.
Can you imagine living in the 1790s, walking down the road in your heavy wool clothes, sweating and stinking, because that's what they all did, and seeing some dude hanging little sets of frog legs along his fence like Christmas lights?
For some reason, I imagined that now, like in the current time period.
Well, thank God that guy was jealous.
I feel
Because
like
then
that
we
would be
have
more
to
normal
just
now.
remote the TV.
I've actually done very similar experiments in
I was
lab. Yeah, and we did one with where we kept a frog heart beating, and then we washed it with various solutions to see whether it increased or decreased the BPM. And you know what was weird is we tried all kinds of things. We had all different solutions, and we had a caffeine and a nicotine, and it was the caffeine that made it just suddenly stop. Like it just quit. Like that was it. It was done. But maybe could we tried 10 other things first? Yeah.
Why do I feel like hanging headless frogs on a fence would be more normal now than it would be back
You may be right. You may be right.
Because back then you could at least play it off that you were like, oh, I'm doing this ninja. But if you are laying dead headless frogs on your fence in your neighbor, like, dude, what are you doing? And you're like, making a battery.
You guys. So frogs are used still in biological research and laboratory for a number of reasons. They're used because they're cheap, they're easy to take care of, their reproduction rate is fairly quick, so you can keep a stock of them, and you can just have a tank full of them. Typically, it's the fully aquatic ones. Reina pippins was the species we had, and we had just a massive tank full of Reina pippins. You need some, go get some. But also, they're good because they're easy to dissect, they're small, they're portable, they're all these things, but also because their fertilization process for reproduction is external. So they're very good for any kind of embryological data. Now, to get the embryological experiments with frogs, it's great because you can actually watch, you can watch tadpoles grow, you can watch the little eggs hatch, all that kind of stuff. You give the female frog an injection of a hormone which causes her to create a lot of eggs, and then it's the weirdest thing, but my professor would take this little female frog and she would fold the little frog's legs up like this beside it and stroke down, and all these eggs just came flying out. They just come oozing out, squirting eggs out one after another. So, but you could use the same female frog more than once because the process, she didn't die during the process, but the male frogs, you had to dissect and remove their testes and then chop them up. I'm not kidding. Chop them up in a little dish. I know that sounds horrible. You chop them up in a little dish with some solution, and then that's how you get all the little frogs sperm free to put on the eggs.
That would hurt so bad.
Well, it's already dead, so. But here's a cool thing. Since it's about, but wait, for real. Since it's about to be spring, wait, hold on. I'm gonna tell you something cool. Since it's about to be spring, you may be out walking around and see frog legs on water, right? You ever seen them laying on water? Because they float. Okay, so here's the cool thing. When a frog egg is fertilized, so it's a clear jelly ball with a black dot in the center, right? When a frog egg gets fertilized, the instant it's fertilized, it will flip and the little black dot will rotate exactly to the center at the top. You can watch it happen. It is really cool. So we would take the little chopped up testes and then you squirt it on the eggs, you put them in a solution. Actually, you do something first called dejellying, where you put all the frog eggs with the jelly in a solution and swish them around so that they're not all stuck together, because they're all stuck together. And then you can take some eggs and put them over here, and you take sperm solution and you squirt it on the top and you watch them. And in a matter of minutes, they go whoop, 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 and they all turn and point up. So if you're walking around in the spring and you pass a pond and there's frog eggs and they're pointing up, those are developing eggs. They have been fertilized. A male frog has come by and visited, as opposed to, because they can lay eggs that don't get fertilized. So you may see them everywhere, but if they're pointing up, it's the coolest thing to watch because you can just watch it happen. And you're like, I just watched life being created right there. Just bing. It's really neat because you don't see that with mammals because it's internal. So it's pretty cool to see it externally. No, we saw that. It was creepy. All right, so your homework. Was it keep in binder? I can't remember.
No, it says do.
Was it? I couldn't remember. All right. If you still have it with you, we'll look over. Good. All right. So, yeah, turn in if you want to turn it in. I mean, if you've turned it in and you want to get it, grab it. So here we go. And that was not supposed to show me already. Don't do that, dummy. All right. So section 1, you had this question number 6. Assign oxidation numbers to the atoms in each of the following. There we go. So did anybody get letter A there? Want to share what they got?
We did +4.
+4. Okay, so your H is a +1, your S is a +4, and your O is a -2.
So
yeah.
Well, it was wanting to break it down by each of the atoms. So, right. Mm-hmm. You're fine. And then your chlorine, because it's alone, remember if it's a solid and it's alone, it's just gonna be 0, right?
Yeah, that's what we got.
Good. So what did anybody get over here?
We didn't break it up by atom.
Oh, you did the whole thing. Okay. So if you're breaking it up by atom, this would be what you'd get. And you can write it down if you still have your paperwork with you and you want to change it before handing it in, that's fine. And what did anybody get for D?
Would that be +2?
So you got a +5 and -2. And I'm not going to test you on this kind of stuff, but I wanted you to give it a try. Give it an old college try. Take a stab at it, right? That's fine. That's the thing with homework. Unless you don't try or you give an answer that's so ridiculous that I'm like, I don't count off for it because that's what it's supposed to be. It's supposed to be giving it a shot. So our next question asked that one showed up early. So which of the following equations represent redox reactions? And then for each reaction, determine which atom is oxidized, which is reduced. So B and C are redox, and A and D are not redox, is right. Okay, so with the first, why are these out of order? All right, well, we'll just do it. Oh, because it's in order. So here's your redox. So your oxygen is oxidized, -2 to just O. And then NO3 negative is the reducing agent. And on this side, your nitrogen is reduced from +5 to -3. So NO3 negative is the oxidizing agent.
So how do we find our oxidizing or reducing agent?
So if you go through all of the steps, like on that toolkit thing, where it shows you the numbers, once you know the oxidation numbers, you can tell what's oxidizing and reducing because you can tell what's gaining and
Find
losing.
the oxidation numbers of every atom in every part of the equation.
Right.
And compare the oxidation number of the same atom
On the other side, and you can tell if it's gaining or losing electrons. But this is where like breaking it down into half equations and half reactions are, and all that does help. I just wanted y'all to take a stab at it. So in this case, we've got H2 by itself and it's a gas. So we know it's going to be 0, right? So it started out at 0 here, but it goes from 0 to +1. So that means it's reducing. reducing agent, sorry. And then copper is being reduced. So it's the oxidizing agent. And then the last one is not a redox. So I'll give you a minute to write them down. Actually, if everybody does everybody have it on them right now? I see yours, Alex, and you have yours, Jack, over there.
What?
You have your homework there.
Yeah, mine's right here.
You got yours, Sydney? If I see that you're doing them and you're copying these down, then I'll just check them off and you can keep it in your binder. It's one less thing for me to do, one less thing for you to worry about getting back. So you don't need to if I'm looking at it right here. And I know everybody's writing down the same stuff.
What does it say for the last one?
It's not a redux.
Okay. It's not, well,
That would make sense because I got zero.
yeah, oxygen did oxidize, but nothing else did.
Yeah, that was the thing I kept having a problem with.
Yeah.
All none of them had any pluses or minuses, and based on the rules I was seeing, they all seemed like they would have equal zero.
Yeah, I know what you mean.
Even then, though, I think, yeah, I mean, maybe.
So it goes back to that one where it was like, how do you know if it's a redox equation? And there were a couple of specific things. I'll go back to that slide again when we finish. Everybody have all that? Everybody got it? Yes? Okay, cool. So then there's this one. If you wanted to use an electrochemical cell to deposit a thin layer of silver metal onto a bracelet, which electrode would you make the bracelet? And explain why you do it.
Yeah, I don't know how to solve the question.
Uh-huh.
I looked it up, I got either silver or copper.
Okay,
But I understand how.
so it's wanting to know which electrode
Believe it was
you
like
use.
cathode, something like that. Right, yeah,
So
put down
you do
cathode.
the cathode, and it's because depositing silver onto the bracelet requires the reaction of the silver and the electron. So the silver takes place on the bracelet. So the reaction, it's a reduction reaction, which happens at the cathode. If you want to watch something cool, maybe if there's time, we'll do it. There is a how it's made on metal plating, and it's great.
Yeah.
I don't know if it's in next week's lesson for you or not. I know I put it in for the juniors, but I can watch how it's made all day. Like I can binge how it's made. That is a fascinating.
I remember the inputs of it like that.
Yeah, I wish it was still on TV and they were still doing new stuff, but
They're not.
I don't think so. They were fabulous. I love how it's made.
I
Oh,
remember
yeah, it was.
just
I love
a
it.
little after
It's like-
you just watch it.
I love the door.
I remember when they made videos stuff, so I
Make sure everybody's got it.
Oh, yeah. I didn't want to. Like they built
I had that.
so like I remember the welcome call, they were like $10,000.
I don't know why I did this.
Yeah.
Why?
One tree house, the tree house.
I don't know.
Tree house.
Why?
Ooh, look at that Vareo.
Yeah, I like tree house.
There's a pretty little bird out there. Oh, Vareo.
Um,
There's our state bird on my bird feeder.
Oh.
Thrasher.
It's just like nose time.
Thrasher. I got for my birthday one of those, it's not the horse, it's the unicorn, but it's the head that you put the food in and they put it where the squirrels can get to it and they have to go inside. It looks like they have a giant horse head or whatever. I need to get that hung up because I can't wait. That sounds
it's
so hilarious. It's a unicorn head.
How-
Yeah.
Food, and
You put food in it and the squirrel gets in it and he's wearing a head.
We need that.
I know. I have to figure out how to, that's a Vareo on top.
I need that in my
They're
life.
beautiful. All right, everybody have all this one? We have it? Bailey's still
Yeah.
rating? Okay, let her finish.
Oh, I'm more concerned with this.
And it's bizarre. We brought a trivet to class. I don't know why.
What is that?
It's a trivet.
I was using it because,
We can probably.
well, I brought this and this was warm and it like got warm and I.
Whatever works for you, man. You got it, Bailey? Okay. So that was it, right? For y'all for homework. So this week we are, wowie. Whoops. Wrong one. Open the, thank you. Lord have mercy. So looking ahead, Y'all are absolutely nuts, but it's why I love you people.
We are, thank you.
It's why I love you people. Looking ahead, we are not quite there yet. Almost
Those
here.
are cheeses, my guy.
So next week is lesson 28. So you don't have to turn in, guys, you don't have to turn in the lab from this week, right? We're not turning in the lab from this week, but you are going to, I'll put the video together and I'll probably require you to just comment so that I know that you see all the data combined and put together. Yes.
Which lesson's the WebQuest lab?
It is the one that's nuclear chemistry. So it's 29.
Okay.
So it's when you come back from spring break, which is what I was going to say. So today we did 27. Next week is 28. All right. And we'll be wrapping up electrochemistry. You'll have a test, but your
So the
test will not be due till you get back from
So
spring
the
break.
week after next is spring break.
Week after next is spring break. It is 2 weeks because of the way Holy Week fell. So next week we are doing electrolysis, which is a super fun lab to send off to spring break with because it's just cool. It's just really, really cool. And then we are doing the WebQuest lab when you come back. So don't forget to bring devices for that. Then we've got
Wait, didn't break start this week?
not this lesson, after next lesson, after 28, between 28 and 29. And then when you get back, we're doing our toy balls and polymers lab where we're going to make bouncy balls.
Yes.
And then we're doing the DNA lab, and that's it. We're done with labs. So there are not that many left. You will have to turn in so that you know, not this week's lab, obviously, which we were just saying. Next week's lab, the electrolysis, you will also keep in your binder. You won't be turning that one in. You won't be turning in the WebQuest one, but you will be turning in the polymer lab. So that will be the last one that you'll be turning in. The others are all wrap up in class, keep in your binder. Yes.
Will we get to take home the bouncy balls we made?
Yeah. One more thing. So there are 2 DNA labs. The first one, this DNA RNA game, is a game we're going to play. It's actual involves cards, and it's about DNA nucleic acid bases. So it's for the base pairs for the nucleic acids. So you'll be practicing matching base pairs. Does anybody know about like the DNA base pairs anyway? Anybody have any background on that or done it? So you have your 4 nucleic acids that comprise DNA, and there are 4 that comprise RNA, but there's one that's different between the 2, and they always match a certain way. So we'll be doing that. And then, yes.
It says next week's homework is keep in binder. Is that?
Yep, if that's what I wrote. Yep. So next week's homework is, keeping your binder. A lot of these homeworks from here on out are going to be, some of them will be book questions like this, and some of them are going to be more like think questions, like research this and tell me what you find, especially the juniors have a lot of those because they don't have a nuclear chemistry unit. They don't have an electrochemistry unit. So I had to write all of their curriculum. But as we're coming up on DNA, definitely start thinking about, I'll tell you this, it's super cool because I think I go over it with the juniors a little bit more than you guys, but there's been some real, and I want to take down elements before everybody's done, but there have been some real advancements in DNA lately that have been really essential in solving some cold case stuff.
Yeah.
And you hear about that a lot, but there has been a lot with familial DNA, because now everybody's doing 23andMe and Ancestry.com, and they're throwing their DNA out there, and say you can't find a perpetrator, but you have his DNA. And if you're able to plug that into a system and see who the relatives are, well, now you've narrowed down your situation a lot. There are all kinds of laws and rules that surround that with Ancestry and 23andMe, because those are private companies where you agree that if you give your DNA, they're not going to give it to the police, like if they want. There's a whole thing. But there's another website called GEDmatch, and GEDmatch is open source essentially. So because of that, that can be used for research in a different way.
If you think that
And then- Yeah. And then there's another, well, that's how they caught the Green River killer, who he'd been, I mean, it'd been years, and it was a cold case for a good long time. And they actually found his brother through GEDmatch and realized that he was on their initial suspect list. Once they found the brother, they're like, well, who are his relatives? Oh, that guy, he was on our initial suspect list. So then when they thought it was him, they followed him around until I think he threw a cup away or something, and they grabbed it. Because if it's in the trash, they can take it. They don't need a warrant for that. The other one I was going to tell you about, which is definitely interesting to look into, is there's a company called Parabon out of, I think they're in Northern Virginia, but they're doing something completely revolutionary. And they've only been doing it for about 2-3 years now, but it's DNA phenotyping. So what they're doing is they're taking DNA from like a Jane Doe, for example, and putting it into their system, and it produces a composite image of that person's face based on their DNA, which is wild and not something we ever really imagined would be a possibility. But some of them are freakishly spot on. Like they've done it just as samples to see what the computer spits out. Because usually you have a composite artist and you talk to them and describe things and they draw faces, or they do the reconstructions from skulls or whatever, and they construct an image and put it out to the world and say, we think this is what this person looked like. But these are incredibly good.
Now
It's
imagine
freaky.
using that on the perpetrator's DNA. You can get a hold of some of that.
Yeah, well, and that's the
You
next
use
thing.
that and then run that through.
They actually have done that. They actually have created a couple where we think we're looking for somebody who looks kind of like this. So it's freaky, but it's unbelievable what they're able to do, because they can tell certain things they can tell like, your ethnicity, but they can also tell your approximate height, and it's a range, but they can tell if you're likely to be short or tall, whether or not you're likely to be heavy set or thin, all of that. Like there's definitely a range, that there's a nature versus nurture thing, right? There's definitely environmental factors, but a lot of that's coded right into your DNA. And are you likely to have curly hair or straight hair? What color are your eyes? Do you have freckles? Like all of this stuff they can.
Hair color, although that's easier to change.
All right, so tell me, Alex, what element are you doing? Do you know yet?
I know.
Don't know.
No, I have a few that I'm looking at.
Okay, well, whatever goes on here today is claimed.
I
So,
believe Shannon was doing.
Shannon drinks sodium.
Yeah.
doing sodium, and she's doing it for you. Okay, so let me put that here.
Oh, you and I work together. Bailey wants to work with me.
Yeah.
Yeah.
And what are you guys doing then?
We don't have an element yet.
Okay,
We were gonna do that later today.
Yeah.
all right. Michael, do you know what you're doing yet?
Yeah, I do neon.
Neon. I did that one when I had to create one of those awful boar models when I was a kid, and I painted it all neon. Sid wants lead, right? All right, and who else? Was it 3 of you together or just you? Okay, Abby wants bismuth. That's an interesting choice. What you got? You guys were doing one together, and it was what?
I did silver.
I think you both were doing it, weren't you?
Maybe.
I think your mom said Lily and E. Silver, that's right. Okay.
I might end up doing it.
Okay, we'll see. Cole, do you know what you're doing? Okay.
Maybe.
I don't think any of the other juniors have claimed anything yet, but I will put that out and make sure that we're all good. So you have normal work this week, normal homework, no lab that you have to turn in. I will ask you to comment. I will make that obvious for you. Next week, your homework, just so you see it, if you don't have it in front of you. Oh, no, not that. We finished Q2 a long time ago, man. Also, be sure that you check your teacher E's. Some of you do owe me some stuff still. Be sure you don't owe me anything, because I would love to close Q3. It would make my day. So yeah, this is more questions from your book. There you go. Alrighty. Anybody have any questions about today? Are we all good? We good? All right, y'all. Close this one out later.